Our galaxy is moving towards something we can't see. Not slowly, not gently. The Milky Way is being dragged through space at roughly 2 million miles per hour toward a region of the universe that has no obvious cause, no confirmed object, and no agreed explanation. And the strangest part isn't the speed. It's that we've known about this for decades, and we still can't fully explain it. Most people picture our galaxy as floating, stable, maybe drifting a little, the way a leaf rests on still water. That's the comfortable version. The textbook picture showed a universe expanding in every direction, more or less equally, galaxies spreading apart like dots on a balloon being inflated. In that picture, there's no preferred direction, no pull, just expansion. Then the data started coming in, and the picture broke. Before this video is over, we'll come back to the number that forced astronomers to stop calling this a measurement error and start calling it a problem. Let's start with where this discovery actually came from, because it didn't begin with a supercomputer or a space telescope. It began with a refrigerator. In the 1960s, two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, were trying to clean up noise in their antenna. They found a faint microwave signal coming from every direction in the sky with almost perfect uniformity. That signal turned out to be the cosmic microwave background, the afterglow of the Big Bang itself, the oldest light in the universe. It earned them the Nobel Prize. For the next decade, scientists treated this radiation as essentially smooth, same in every direction, a near-perfect bath of ancient energy left over from the first moments of the universe. Then, in the 1970s, something annoying appeared in the data. A tiny variation, a slight warming in one part of the sky, and a slight cooling in the opposite direction. At first, physicists assumed it was an instrument error. Then they checked again and again. The variation was real, and it was consistent. It wasn't random static. It had a direction. What they were seeing is called the CMB dipole, the cosmic microwave background dipole anisotropy. The word anisotropy just means not the same in all directions. The variation is tiny, less than 1 part in 1,000, but it's there, and it points somewhere specific. Here's what causes it. When you move through a sea of radiation, the radiation in the direction you're heading looks slightly warmer. The radiation behind you looks slightly cooler. It's the same effect that makes a rainstorm seem to be hitting your front windshield harder than your back window when you're driving. You're moving into it. So the CMB dipole tells us the Earth is moving relative to the ancient bath of light. That makes sense on its own. The Earth orbits the Sun. The Sun moves through the Milky Way. None of that is surprising. But when astronomers subtracted out all the local motions, the Earth's orbit, the Sun's path through the galaxy, they found something left over. The Milky Way itself, our entire galaxy, was moving fast. The speed they measured was staggering, roughly 600 kilometers per second. That's about 1.3 million miles per hour. Later refinements pushed estimates higher, somewhere in the range of 630 to 650 kilometers per second. That's approximately 1.5 billion miles per hour. Some analyses of large-scale galaxy flows put the combined motion even closer to 2 million miles per hour when accounting for the full chain of gravitational influences. 2 million miles per hour. Towards something. The question was what? In 1987, a group of astronomers calling themselves the Seven Samurai, this was actually their informal name, published a landmark study of galaxy velocities. They mapped the motions of hundreds of elliptical galaxies across a wide region of sky. What they found was that galaxies were not simply flying apart from the Big Bang. They were being pulled, collectively, toward a specific region in the direction of the constellation Centaurus. They gave the source a name: the Great Attractor. It sits roughly 250 million light-years away. That's a distance so large that raw numbers stop meaning anything. So, put it this way. If you shrunk the Milky Way down to the size of a grain of sand, the Great Attractor would still be the length of a football field away. And here's where it gets stranger. The region the Seven Samurai identified is not just pulling us. It appears to be pulling everything in the local neighborhood of galaxies. The Milky Way, Andromeda, dozens of galaxy groups across a region hundreds of millions of light-years wide, all of them streaming in the same direction. That's not what gravity from a single cluster should look like. A single massive cluster could pull its immediate neighborhood. What the data showed was a coherent flow of material across a scale far too large for any one object to explain. Something bigger was at work. Now here's the complication that nearly buried the whole story for a decade. The Great Attractor lies directly behind the plane of the Milky Way. Our own galaxy's disk, the gas, dust, and stars of the Milky Way, blocks the view. Optical telescopes couldn't see through it. When astronomers pointed their instruments toward the source of the pull, they were staring at their own galaxy's crowded backyard. This zone is called the Zone of Avoidance. Not because astronomers avoid it for convenience, because for most of the 20th century, the dust and gas of the Milky Way made it nearly opaque to visible light. Whatever was on the other side was hidden behind a wall of our own making. Radio and X-ray telescopes eventually began punching through. In the 1990s, observations in these wavelengths started revealing what lay behind the galactic plane. What they found was a supercluster of galaxies centered on a region called Norma, the Norma cluster, Abell 3627, a massive concentration of galaxies sitting at roughly 220 million light-years. By some calculations, it was 5,000 times the mass of the Milky Way. 5,000 times. And yet, when astrophysicists ran the numbers, the Norma cluster wasn't big enough, not even close. Its mass could account for some of the observed flow, not all of it. Something else was still missing. This is the part that should bother you. Astronomers had found the thing, the large object they'd expected to find, and it still didn't explain the full motion. The galaxy kept flowing faster than Norma alone could pull it, so the search widened. In 2016, researchers using the Parkes Radio Telescope in Australia published a study identifying a new structure even further out. They called it the Vela supercluster. It sits roughly 800 million light-years away, far beyond the Norma cluster. And it's enormous. Early estimates suggested it could rival the most massive known structures in the universe. The Vela supercluster had been hiding in the Zone of Avoidance. Once researchers mapped it in radio wavelengths, they found it contributed meaningfully to the observed flow. Maybe 10% of the measured velocity, maybe more. But that still left the majority of the motion unaccounted for. Here is where the story splits into two competing explanations that researchers are still arguing about today. The first explanation says the pull is real. There is a massive concentration of matter, possibly multiple overlapping superclusters, possibly a structure we haven't fully mapped yet, generating genuine gravitational attraction. The universe is lumpy at scales we haven't fully surveyed. We're being pulled toward a dense region. We just can't see it all yet because the zone of avoidance is still partially opaque, and because mapping structures hundreds of millions of light years away takes decades of telescope time. The second explanation is considerably weirder. Some researchers have proposed that we're not only being pulled toward something, we're also being pushed away from something. In this picture, the Great Attractor isn't the full story. There's a vast region of below-average galaxy density behind us, a super void that's effectively pushing the local group forward by reducing the gravitational drag from that direction. In 2017, a team led by Yehuda Hoffman at the Hebrew University in Jerusalem published a study introducing a name for this supposed pushing zone: the dipole repeller. The idea is counterintuitive at first. A void doesn't push anything, it just pulls less. But when everything around you is pulling equally in every direction, a void in one direction means less pull from that side. The net effect is motion away from the void toward the denser region. It looks like a push. The dipole repeller, in this model, might be contributing as much to the Milky Way's motion as the Great Attractor is. We're caught between two forces, a pull from the front, a comparative void from behind. This model fits the CMB dipole data better than pure attraction alone, but it's still contested. The supervoid itself is difficult to confirm directly because measuring the absence of matter requires mapping an enormous volume of space with enough precision to say confidently that the density there is genuinely below average, not just poorly sampled. Stand in your living room for a moment. Look at the ceiling. You're sitting on a planet orbiting a star inside a galaxy that's inside a local group of galaxies that's inside a supercluster called Laniakea. All of that, every bit of it, is currently streaming at roughly 2 million miles per hour toward a region of the sky near the Southern Cross. The floor beneath your feet is not still. None of this is still. The stillness is an illusion that only works because everything you can see is moving with you. Now let's talk about Laniakea, because this is where the story got a genuine reframe. In 2014, a team led by Brent Tully at the University of Hawaii published a paper in the journal Nature that redrew the map of our cosmic neighborhood. Using a technique that combined galaxy redshifts with their peculiar velocities, the motions that deviate from pure Hubble expansion, they identified the full watershed of gravitational influence that the Milky Way sits inside. They named it Laniakea. In Hawaiian, the word means immeasurable heaven. Laniakea spans roughly 500 million light years and contains the mass of about 100 million billion suns. It includes over 100,000 galaxies. And the Milky Way is not at its center, it's near the edge. The Tully team showed that all the galaxies inside Laniakea are flowing inward toward a common center of attraction, which sits, roughly, in the direction of the Great Attractor. This was the first time anyone had drawn a coherent boundary around our cosmic supercluster and shown the internal flow pattern. But even Tully was careful about what this meant. Laniakea doesn't explain the pull. it describes it. The flows within Laniakea are the result of whatever gravitational landscape lies beyond it, including whatever sits at the source of the Great Attractor pull, and that source is still, fundamentally, unconfirmed. Here's the number that forced the scientific community to take this seriously as a genuine structural mystery rather than a data artifact. The CMB dipole, the variation in the ancient cosmic radiation caused by our motion, has been measured with extraordinary precision by multiple independent instruments. The European Space Agency's Planck satellite, which mapped the CMB from 2009 through 2013, produced the most precise measurement ever made. The dipole it measured corresponds to a velocity of 627 kilometers per second toward a very specific point in the sky. Right ascension, 10 hours, 48 minutes. Declination, minus 28 degrees. That's in the direction of the Hydra Centaurus region. That number, 627 kilometers per second, didn't move between independent measurements. It showed up in the COBE satellite data from 1992. It showed up in the WMAP satellite data from the early 2000s. It showed up in Planck data from the 2010s. 3 independent satellites, 3 different instrument designs, 3 separate teams, the same answer every time. That is not a measurement error. There's one more layer to this, and it's the one that cosmologists find most uncomfortable. The standard model of cosmology, called lambda CDM, which stands for lambda cold dark matter, predicts that the universe should be statistically uniform at the very largest scales. Smooth out. Yes, there are clusters and voids at medium scales. But at truly large scales, hundreds of millions to billions of light years, the distribution of matter should look roughly the same in every direction. The flows we're seeing challenge that assumption. Several recent studies have found that the CMB dipole, when compared to the motion inferred from counting distant quasars and radio galaxies, shows a potential tension. The number of objects in one part of the sky doesn't quite match what you'd expect if the universe is truly uniform at large scales. This is sometimes called the CMB dipole tension, or the kinematic dipole debate, and it's one of the most quietly controversial topics in modern cosmology. Some researchers have proposed that this tension points to something genuinely unexpected in the large-scale structure of the universe. Not just a cluster or supercluster we haven't found yet. Something about the geometry or the matter distribution at scales approaching the observable horizon. That's a significant claim. It's not proven, but it hasn't been disproven either, and several independent groups have now replicated the underlying signal. The Milky Way's motion is not in isolation, the strange part. Large-scale flows exist throughout the observable universe. Matter clumps, voids form, gravity does its work across billions of years, and you get motion. That's expected. What's strange is the scale of what's needed to explain our specific motion. The structures required are at the edge of what current surveys can confirm. The zone of avoidance still hides a significant fraction of the relevant sky, and the measurements keep coming back sharper and more insistent, pointing at the same patch of sky, demanding an explanation that cosmology hasn't cleanly delivered yet. The Norma cluster is real. Laniakea is real. The Vela supercluster is real. Each of them contributes to the flow, and together, they still don't close the gap. Whatever is pulling us may be a structure so large that it barely fits within what we can observe. It may involve the dipole repeller working in combination with massive foreground attractors. it may ultimately resolve into a dense wall of matter that radio surveys simply haven't fully sampled. Or it may be pointing at something about the large-scale structure of the universe that the standard model doesn't predict well. That's the honest position. Not that we have no idea, we have many ideas, and the data is good enough to test them. But the ideas don't yet converge, and the universe, as usual, is under no obligation to hurry up and simplify. The granite that shouldn't be there, the mass that doesn't match, the flow that's too coherent, too wide, too fast for any single known object to produce. The universe isn't broken. Our map of it is just not finished yet. 2 million miles per hour towards something real, in a direction we can measure to 4 decimal places, and we're still figuring out what's on the other end of the line. Thanks for watching, and I'll see you in the next one.